Here we introduce the simple feedforward network. While NLP makes use of many more complex architectures, RNNs, transformers, attention, the feedforward network is still an important tool and underlies these more complex architectures. A feedforward network is a multi-layer network in which the units are connected with no cycles. The outputs from units in each layer are passed to units in the next highest layer, and no outputs are passed back to lower layers. For historical reasons, feedforward networks can also be called multi-layer perceptrons, or MLPs, although they aren't technically composed of perceptrons anymore. Simple feedforward networks have three kinds of nodes: input units, hidden units, and output units. Let's go back to logistic regression. We can think of binary logistic regression as a one-layer network. We don't count input layers when we're counting layers, so we'll call this input layer, layer 0. And so this is a one-layer network. So we have an input layer we could call layer 0, consisting of a vector x. We multiply x by a weight matrix, W, add a scalar b, and then the first layer, the output layer, computes a scalar y by applying a sigmoid to wx plus b. So simple logistic regression viewed as a network. And remember multinomial logistic regression, where instead of a single sigmoid at the output, we had a softmax that turns the output values into probabilities. So we'll get probabilities over discrete outcomes. Where before W was a simple vector, now W is a matrix, and where B had been a scalar, now B is a vector. So now we're multiplying the weight matrix W by the input X, adding a vector B to produce a vector over possible outcomes. Remember that the softmax is a generalization of the sigmoid. So the softmax of a vector Z replaces each element with an X over a sum of X. So for example, if we have an input vector Z, that's just a set of scores, some positive, some negative values. Running it through a softmax will produce a set of probabilities that will sum to 1. So softmax, very convenient output function. Logistic regression is a one-layer network, but the power of neural networks come when we have a hidden layer. So minimally two-layer networks. So here's a two-layer network, the input layer, layer 0, a hidden layer, layer 1, and an output layer 2. And here are the equations for a feed-forward network with this single hidden layer. Takes an input X, multiplies it by the weight matrix W, and adds a bias. So each element, W sub ji, of the weight matrix W represents the weight of the connection from the ith hidden unit X sub I to the jth hidden unit H sub j. We're showing the activation function here as sigma. So we have the hidden unit is sigma of Wx plus b, but the activation function could be a ReLU or a tan H, as we've talked about earlier. And notice that we're applying that H is a vector, and we're applying sigma to a vector, Wx is a vector. So we can apply a function like sigma to a single value or to a vector element-wise. Now, as we saw in the lecture on XOR, the resulting H value, hidden value, forms a representation of the input. Now, then the role of the output layer is to take this new representation H and compute a final output. This output could be a real valued number, but in many cases, the goal of the network is to make some sort of classification decision, and so we'll focus on this case of classification. If we're doing a binary task like sentiment classification, we might have a single output node, and the value y is the probability of, say, positive versus negative sentiment. So the output layer has another weight matrix U, and many models don't include a bias vector B in the output layer, so we'll just simplify by eliminating the bias in this example. So the weight matrix U is multiplied by its input vector, which is the vector H, to produce the intermediate output Z, and then we use the sigmoid to turn this into a probability. What if you have more than two output classes? If we're doing multinomial classification, like assigning a part of speech tag, we just add more output units, one for each class. So we might have one output unit for each potential part of speech, and the output value is going to be the probability of that part of speech. So the output layer gives a probability distribution across the output nodes, and we use the softmax to compute this distribution, just as for multinomial logistic regression. That means we can think of a neural network classifier with one hidden layer as building a vector H, which is a hidden layer representation of the input, and then running a standard logistic regression on the features that the network develops in H. By contrast, when we presented logistic regression, the features were mainly designed by hand via feature templates. So a neural network is like logistic regression, but with many layers, since a deep neural network is like a layer after layer of logistic regression classifiers. And rather than forming the features by handwritten feature templates, the prior layers of the network induce the feature representations themselves. Let's now set up some notation to make it easier to talk about deeper networks of depth more than 2. We'll use superscripts in square brackets to mean layer numbers, starting at 0 for the input layers. So W super 1 will mean the weight matrix for the first hidden layer, and B super 1 will mean the bias vector for the first hidden layer. And we'll use G to stand for the activation function, which will tend to be ReLU for intermediate layers, and softmax for output layers. We'll use A super I to mean the output from layer I, and Z super I to mean the combination of weights and biases. The inputs will refer to more generally as A super 0. Thus, we can re-represent our 2-layer network with these equations on the right. Here they are written out together. Notice with this notation that the equations done for the computation at each layer, layer 1 and layer 2, are the same. So the algorithm for computing the forward step in an n-layer feed-forward network, given the input vector A super 0, is thus simply to go through the layers, computing our z's as our w dot a's plus b's, where a's are the inputs from the previous layer, and then our output to the current layer is our nonlinearity of the z's. And then at the very end, our estimate y hat is the output of the last layer. In describing networks, we'll often use a slightly simplified notation that represents exactly the same function, but without referring to an explicit bias node B. We'll do this instead by adding a dummy node A sub 0 to each layer whose value will always be 1. Thus, layer 0, the input layer, will have a dummy node A sub 0 super 0, value 1. Layer 1 will have A sub 0 super 1, to value of 1, and so on. And the weight associated with this dummy node represents the bias value B. So instead of our input being x1 through x n sub 0, where n sub 0 is the number of units at layer 0, we'll add an extra unit x sub 0. And instead of talking about sigma of wx plus b, we'll talk about sigma of wx. But if we break down this computation, instead of wx being the sum from 1 to n sub 0 of the weight times the input value, it'll be the sum starting at 0 because of this extra bias value. So instead of having an extra bias term b, we'll simply add our value x sub 0 and subsume b into the weight matrix w. We'll continue showing the biases b for the learning example in the next few lectures, but afterwards, we'll switch to this simplified notation without explicit bias terms. We've now introduced feed-forward neural networks, the most basic neural network architecture.